Okay, so good afternoon to everybody. This is our today's topic. We will be discussing differential amplifiers, starting from basic, their definition, how they will work, and some of the design related issues. And there are some topologies, some important topologies of differential amplifier. Those who are mostly using today's analog CMOS designing. And if time permits, then I may discuss a design of a simple diff amp. Let us see how far we can go. So first, that what is a differential amplifier? There are two definitions for that. One is a generic definition amplifier that amplify difference between the two signal. That is just say, I mean, the common thing, or layman's definition of the differential amplifiers. But another definition is that it is amplifier whose response is an odd function of their input. I mean, odd function means we have we can write that V out of anything, of any system, as some a series of polynomial of alpha 1, alpha 2, like that. So if for a system our these alpha alpha 3 V in cube goes on. If for a particular system these alpha 2, alpha 4, these coefficients are 0, alpha 6, I mean all even coefficients are 0, then the system exhibits a differential behavior, differential amplifier type of behavior. And the most generic wave or function showing like this is a tan hyperbolic, tan h of something. It will be like this. This is output, input, and it can be shown that if we use BJT input device, then our output is a some constant will be here, some V0 or something. Okay, some constant will be there, A, and tan hyperbolic of output A is a tan hyperbolic function of V input divided by Vt, where Vt is a thermal voltage, that beta by Kt or like that something. So for BJT this is true, and even for CMOS, though we don't have this tan hyperbolic kind of behavior for MOSes, but we have this kind of structure, basically this kind of wave shape between input and output for a differential amplifier. And you see that an odd function means also that f of minus x is equal to minus of fx. Like this. Well, that it can be other way around also. This way also, this is also odd function. You can have this V in or V out. Actually, that depends on how we are taking the output. So depending on the that reference, that shape of the function changes. Sometime it likes the, and sometime it is one. But mostly we will be following this one. Only for a one case is there which uses active current mirror as a load, that shows this kind of positive slope of transfer function. So this regarding the definition of the differential amplifier. The question is how, why do we need basically differential amplifiers? Because yesterday, in the last class, we have studied single stage amplifiers. We have studied number of topologies of that. But why do we need diff amps? Actually, the trend is that the VDD, the supply voltage, is gradually decreasing. It starts decreasing from 10 volt to 12 volt. Now we are using 1.8 volt. Even 1 volt, using 1 volt VDD, some chips have been designed in our lab also. So supply voltage is reducing, and that reduces that swing, the output swing we can get. The maximum output swing we can get is also gradually reducing as a proportional to the VDD. So the output swing is reducing. And do you have any idea about noise? I mean, noise generated by the device and all those things. Okay, the noise is a generic phenomenon. Noise is everywhere, it is present. we cannot nullify the noise, but we can minimize the effect of noise in our device or in our circuits. We can design our circuit in such a way that the noise induced in the signals of the input or in the output will be cancelling each other. So as our one more thing is that we don't have any control over the amplitude of the noise induced, because noise is a natural phenomenon. So we cannot control the magnitude, how much noise is going to be induced in my circuit, but we can minimize the effect of that induced noise further in our circuit. So so our signal swing is decreasing, but the noise remaining fixed. I mean, when we are using 12 volt supply, the noise amplitude induced remains same present day also when we are using 1 volt or 1.8 volt. So the signal to noise ratio is decreasing with VDD decreasing. So and differential amplifier is the mostly used topology, circuit topology, that basically cancels the effect of noise. How it will do that I will discuss. I will discuss later. And the second is that it reduces the power supply variation, because the power supply, the VDD or ground, whatever it may be, the source of VDD may have some variation. I mean, you cannot get 1.8 volt constantly for 2 hours, 3 hours. It may be 1.6 volt, 1.7 volt. Normally, 10% of the VDD variation is a typical thing. I mean, 10% of your design. Suppose you are designing for 1.8 volt, so you have to take into account the variation of your VDD from 1.6 to 2 volt. I mean, the 10% of this thing. So 10% variation is there. And also suppose you are drawing this VDD line in your layout, and very near to that there is a clock. This is clock line, this is your supply. And as you know that clock is a very in fact all digital circuits are most noisy, because the digital thing they are always interested in VDD to 0 to VDD. There is a sharp change in input and outputs of all digital circuits. So the clock is also the main source of induced noise. The clock waveform is like that. It is going from 0 to VDD. And as you know that there are some capacity. This is a metal line, metal 1 say, and this is also say metal 1, and in between them there are some dielectrics. This is single plane. So the clocks are changing here. So there are some parasitic capacitors between these two lines. A distributed parasitic capacitors will be there. So this sudden change in the clock voltage will be induced here. So VDD also, suppose we are supposed to have this flat 1.2 volt, 1.8 volt of VDD. But when this clock changes suddenly from VDD to 0 or 0 to VDD, we may have such these spikes there. So our DFAMs also, DFAMs have a special property that it will reject such power supply variation or noise in the power supply line. And also we have higher output voltage swing, because using a single amplifier we can have maximum. Suppose this is our single stage amplifier, we can have a maximum swing, say some VDD2, maximally VDD2. This is our input. It should be, I mean, that 1 VTH less than this. Suppose the output DC is something is there, V out DC. So the minimum voltage it can go is one threshold voltage less than this thing. Otherwise, it will enter into the triode zone. So the maximum swing we can have this thing. But if we have a differential amplifier, one more is there, that will show like this. And if we take the difference between these two, I mean this output and that output, and take that difference as our new output, draw it here. This is a single stage, this is a single stage. Input we are giving like this. Here, this swing we are getting here, and at this point, call it Vx. This is Vy. Now we define our new V out as a Vx minus Vy. So we are getting basically so this waveform minus this. So basically we are getting a twice the swing it has previously it had, minus this one. So our output swing increases, effective output swing increases. So these three are the main reason why we are using differential amplifiers in our analog circuit design. And explain if that to reduce the noise in the input signal. Normally the diff amp has the input line to the diff amp. They have very narrow. I mean the normally in while doing our layout we put input line to the differential amplifiers very near to each other. So the noise induced, this is called input 1, this is input 2. There are transistors. So the noise induced here in this line is also same the noise induced in this line. The magnitude, because they are sitting very near to each other. So the amount of noise or the shape of noise they are disturbing. Suppose we are supposed to have this signal in V1, but due to noise we are getting this. Here also, if we are supposed to give this as a V2, we will have those similar kind of spikes or those things. So, but this system will take this V in, V1 and V2, V1 minus V2 as their net input. So when we subtract from this V1 to V1 from V2 or V2 from V1, those spikes will be getting cancelled. So those input noise induced, I mean we can reduce the effect of induced input noise, and the same thing is also for this noise due to power supply variation, because the variation in the power supply will have their similar effect on the both of the output Vx. It will affect the Vx same way it will affect the Vy. So when we are taking their difference, those effects will be getting cancelled. So this way we will use this differential amplifiers in our circuit design. There are some terms associated with the differential amplifier. Those terms are like this. First is the common mode voltage. What do you mean by the common mode voltage and the differential voltage? Normally what happens that in every input, I mean whatever it V1, call it V1 and V2, we have a DC one. First we have a DC, and then riding on the DC we have our AC. This is our actual signal, this AC one, and we have this DC to properly bias our input transistors. And suppose V2 we have this one, an equation for this, and also suppose that, okay, I will draw it here. This is a common DC, V1, this is V2. If we write the equation, V1 is some, say it is 5 volt, 5 volt plus sin omega t. V2 is 5 volt minus sin omega t. So these two are our input signals, V1 and V2. We define the common mode voltage as VCM equal to V1 plus V2 divided by 2. So for this case it will be 5 volt. And we define our differential voltage V1 minus V2. Here it will be 2 sin omega t. So you see that differential voltage doesn't have any DC component, but the common mode it is basically the DC of this signal, input signal. So if I plot the differential one, time V differential, it will be like this. This magnitude, this is 2, this is minus 2, this is 0. It was 5, 6, and 4. This magnitude is 4. It is hitting below 4 and going up to 6. So so we can write V1 as VCM plus VDF by 2. and V2 as VCM minus VD by 2. So any input to our differential amplifier can be written in this fashion. Some summation of VCM and some common mode voltage and some differential voltage, and I mean plus or minus this sign. So some VCM will be there and V difference will be there. So this is the thing, and the third is the input common mode range. They call it ICMR. It is that you actually, for a particular differential amplifier, you cannot apply any VCM to that system, to the circuit. There is a limit, and that limit is dictated by the condition that, as I have told in the earlier class, always we want that all our transistors should be working in the saturation zone. So that condition dictates what is the VCM limit we can apply to the circuit. There is a lower limit to that VCM, call it VCM L, lower. So VCM should, our applied VCM should be this, and VCM high, and depending on your circuit topology, this low L, VCM L and VCLH will change. The value of this will change. So this is known as ICMR, input common mode range. This is the range between within which we can apply our input common mode signal. How this can be derived for a particular topic, that I will show later. And also we have the input differential range. Suppose we have a fixed VCM at the input, but we cannot apply a large differential voltage, because that will cause again our input transistor to go into triode region or cutoff. So we similar to this ICMR, we have a range between which we can apply our differential voltage. So we cannot basically exceed that range. And CMRR is the common mode rejection ratio. We can write our output voltage, it is equal to Vx minus Vy. This is our differential output voltage, Vx minus Vy. We can write this as a AD Vin and ACM VCM. What does it mean? As I have said, that we can express each and every input with this CM and VDiff. So I call it VDiff. And both of the input, I mean differential input and as well as the common mode input will be getting amplified by our system, by our differential amplifier, and both of them will appear at the output. This is known, AD is known as the differential gain of our differential amplifier. ACM is the common mode gain. Actually this ACM is it can cause some confusion later. We should call it ACM to DM. What is it mean? If we apply a CM at the input only, suppose our differential signal is 0 at the input, we just give one CM signal, common mode signal. But when we are taking the output, we will see that due to some condition or some mismatch or some other thing, we are getting a differential signal, but we should not get that thing. For an ideal differential amplifier, this CM to DM gain should be 0. I mean no input, no common mode input should appear in our differential output. But in all real cases we have finite values of this. So this CM, basically this one, this ACM DM. I will show you later, there is one more CM is there, okay, that I will discuss later. So CMRR, common mode rejection ratio, is defined as AD by VCM or VCM DM. You can take mod of or 10 base log of all these things, whole stuff you can take. So we want the higher CMRR. Higher CMRR means lower ACM DM. So lower this conversion gain, we will having higher CMRR, or our circuit will reject common mode signals. As basically why we want this, because as I have shown in my earlier diagram, noise is a common mode signal, because magnitude of induced noise in both of these lines will be same. So they appear at the input of this transistor as well as at the input of this transistor also. So so the noise acts as a CM, I mean common mode signal. So if we have some finite value of ACM DM, so that noise will appear at our output. So the whole purpose of our diff amp is to reduce the input noise, is is not there, is becoming invalid. So we always want lower ACMDM and higher AD, or in turn we always try to maximize our CMRR. For ideal case, CMRR is infinite. And similarly, that PSRR also is there. PSRR means it is like CMRR, but here we are AD is there, modulus, but here we have some we call it a power supply to DM. I mean the variation of the power supply will cause some differential output variation. So this gain corresponds to that particular kind of amplification. So this is also known as PSRR, and we always want to have higher value of PSRR. Ideally, this should be infinite because this is 0 for ideal case. And slew rate, that I will discuss later, this slew rate kind of thing. Okay. So these are regarding our basic terminology, and this will be required many times when we will discuss differential amplifier. Okay. So what do we need to make a diff amp? We need 2 input transistors for 2 signal and 2 loads for those 2 transistors. So 2 single stage common mode source amplifiers, I mean not common mode, common source amplifier should be enough to make a diff amp. So in the last class we have studied single stage amplifier. This is one single stage amplifier, this is another single stage amplifier, placed side by side, call it V1, V2, this is Vx, Vy, take this output as our differential output and call this as our differential input. So this is a diff amp. Is it true? That is okay. This circuit basically shows some of these properties. I mean, it shows good value. I mean, acceptable, not acceptable, but some good values of or high values of PSRR, CMRR, and also it gives that twice the swing we want. But the problem with this circuit is different, because see you see just if we are giving some signal here at the input, it is the CM level, and this is our differential input. This is V1 and V2. The same CM, both of them will having same CM. Now suppose, and okay, first for this input we have some output there. It will be like this. So if you are taking the difference of them, you will get a DC value. I mean a swing around DC, not DC, around 0. So this is our net output, Vx minus Vy. Suppose now this CM value has changed to a new value, this input CM value. Okay, let us draw the load line of this thing. This was our previous common mode signal. This is for M1 or M2, whatever it may be, M1 or M2. This was our previous common mode signal, or VCM, and these two are our input swing. It means that input is varying like this one, and we are getting, this is our output. This for Vx. Consider only M1 first this portion, and now suppose this CM value is changed to a new value, like here. Suppose it decreases, it decreases to this value. So our Q point shifted. So output will be new output. We will get a new output, but that will be clipped. Lower end will be as it is, but upper end will be clipped. Okay. So as our input CM changes, our output CM is also changing. So this circuit, this property is known as that output CM is a function of input CM. As our input, is that clear? I mean, if we are changing the input CM signal, which means the DC biasing for VGS, same thing. As this is changing, our output DC or output CM, that is also changing. And As a result of that, we may get some this kind of distortion at the output, some clipped or some non-harmonic kind of things will be there. So to avoid this kind of disadvantage or this phenomena, we can use one constant current source here, and this is the heart of the diff amp. I mean, without the constant current source, diff amps are not diff amp. So now just let us check whether this problem is not is there or not. Suppose the current flowing through this source is ISS. Call it ISS. It is an ideal constant current source. And now, suppose the same signal is same VCM and VDEF is used is applied at the input. Now only consider the common mode properties of this device of this circuit. When there is no signal, only this CM is there. The same CM is here and here, and as both of the branch, both of the side of this circuit is completely matched. These are the same transistors are there. So the half of the current will flow from this branch and the other half from this branch. So we are getting output CM Vx CM is equal to VDD minus PSS by 2 R. R is this resistance. Okay. And similarly for Vy, we are getting this VDD minus this thing. Now, suppose we have shifted our input CM value, but that won't disturb this current, because whatever may be the input CM value, that CM value comes here and here. And if we assume perfect symmetry of the circuit, half of the current should flow through this branch and rest of should flow through this branch. As this half of the current is fixed because we are using a constant current source, so as our output common mode voltage is also fixed. So here output common mode voltage is not dependent on input common mode voltage, and this is an important property of differential amplifier. So these two single stage transistor is not a differential amplifier at all. This is a true differential amplifier with a constant current source. Is that clear? Okay, this discussion. Now, as I have told in my earlier class that it is impossible to get constant current source, real constant current source. We have to use ideal real MOSes or current mirrors to implement these constant current sources, and real MOSes always have some non-ideality, because the constant current source should have infinite resistance across the source. But we know that all our short channel MOSes will have this kind of characteristic. So if we operate for saturation zone, this is inverse of this slope is going to be the output resistance of the source. Okay. So there are some effects of this finite resistance and also using this and also there will be some mismatch between the branches. That resistance and transistors, they cannot be perfectly symmetric or perfectly matched to each other. This is true. Suppose this is 1.1 kilo, it might be 2.1 kilo ohm, but it might be 1.992 or maybe 2.1001. So it is impossible to get exactly symmetrical kind of thing here and here, the resistance and as well as here, because the W by L's maybe here 2, but here 1.9998 it might be. So this mismatch also induces some non-ideal effects to our differential amplifier. There are basically two kind of non-ideal. One is due to the mismatch of this thing, these two branches, and the second one is due to non-ideality of this constant current source. So those two I will now discuss those two effects of this thing. First, take up this thing. We are using a NMOS current source. we can have this current generated by the BGR, band gap generator, band gap reference. This is the current mirror. Sorry, these are all NMOS. So now this acts as our constant current source, this transistor. Call it M1, M2, this is M3. This is our load, Vx, Vy. Now forget about this part, this transistor, this one. Suppose we are giving some external biasing voltage here, Vv, call it Vv. That will hold this transistor in its saturation zone, where it will act as a constant current source. So M3 should be operating here. Okay. But here you see that there is a finite resistance which is inverse of this slope. So we can replace this as a current source, as an ideal current source in parallel with a resistance, call it Rp. And the equivalent circuit for this thing will be looking like this is our GM, transistor output resistance. This is for M1, this is for M2. Here that's this Rp or Rs, call it Rs, not Rp. So this is V1, V2, or it V1 prime, V2 prime, and this voltage V1, this one is V2. Actually this is for M1, that is for M2. V1, D1, S1, S2, I mean source 2, gate 2, drain 2. This is GMV2, GMV1. This is actually the output resistance of the same one transistor, call it R1, call it R2, because now we are assuming both of the branches are perfectly matched with each other. So all GM value and RD value are same, RD, and this is the load, our call it capital RD, I mean R capital D. So if you do some analysis of this circuit, you will be getting this Vx, and this is our Vx, this is Vy. You will get the expression for Vx, and that is a long expression, RD square GMV2 RS RD V2 minus V1. So you will be getting something like this. Is that visible? I mean, can you read these things? Okay. So you will be getting this expression. Now see, this is our differential input V2 minus V1 or V1 minus V2, but the main culprit is here, this V2. So output contains V2 input term, which is not with other terms. I mean such a V2 minus V1 or V1 minus V2 like fashion. And I have already told that we can express V2 or any input as a sum of VCM plus VDIF by 2. So this V2 we can express like this. So input VCM, and mind you, this is input VCM. So some fraction of input VCM is coming at the output. So the whole purpose of this constant current source is getting, is getting invalid here, because in our previously that this one in this circuit we are getting directly the input, the input CM as in the output. Here also we are getting some fraction of this. Why fraction? Fraction by this. This factor will be there. GM RD multiplied with and divided by this fraction. This factor into V2 or VCM is coming at the output. So the effect of this finite resistance is that to reduce or to make output as a dependent of input CM. So if we lower this, suppose if we want to put RS equal to 0, so we are getting to our this circuit. Here the RS is 0, no current source. The source of this transistor is directly grounded. So if we put RS0 here, this point will be grounded. So we are going back to our previous circuit, primitive circuit. So if you put RS0 here, you will get some with RS0 you will get this one, GM RD minus V1 no, I think it is not correct. We will get this one with RS0. So you see that with RS0 only V2 term remains here, and that V2 is a function of VCM. So we are going back to our this circuit, and this circuit contains input C. The output of this circuit contains the input CM level. So the effect of finite resistance is that our input common mode signal is getting amplified or attenuated at the output. Okay. And the effect of mismatch, if you want, suppose after fabrication M1 and M2, suppose after the fabrication of this diff amp, we are getting different GM for M1 and M2. This is GM1 and this is GM2 due to say some mismatch between W by L or like that. This is a constant current source. So the effect of this mismatch, this two GM will be coming at the output. If you draw the small signal equivalent of this circuit and do some analysis, you will be getting output. This output is the net output, Vx minus Vy. Output is this one, RD delta GM. Delta GM means GM1 minus GM2. DCM to RS RD. This is RS RD plus. So this so here what you get, if our input is only CM, our differential input is 0, we are applying only CM voltage between these two, we are getting our differential output as a function of this CM. So ideally this should be 0. If you are not giving any differential input at the input of this amplifier, your output should be 0 for the ideal cases. But here, due to this mismatch, due to this delta GM kind of thing, you are getting a differential output which is a function of input CM. So this gain, rest of the this factor is known as ACM to DM, because this is the gain of common mode to differential mode gain, and our CMRR is defined as AD, differential gain, divided by this gain, this gain. And in my previous circuit, for RS non-zero RS, we have one more CM is there, this one, this factor, because this factor amplifies or attenuates the input CM to the output. This is our Vx, so we can call it ACM. So some people define CMRR as AD versus ACM also. ACM means this one, but CM-DM means this is the gain of the CM to DM conversion. So there are actually two kind of definition of CMRR, but ultimately I think both are equivalent. If you do these things, both will be more or less same. But you should be clearly stating which of the definition or which of the CMRR definition you are following. That should be mentioned. So this is the effect. Similarly, if our resistance is not these two resistance value are not same. Suppose this is RD1, this is RD2. We will be getting some effect of this. We will be getting same function, VCM, but this differential gain will be different. There will be some delta R kind of thing. Delta R means difference between these two, and some this RD square, all those things will be there. So for difference or mismatch between RD, we will be having different ACM DM, and normally people will take this lower value of these two, these or that. This one delta GM or delta RD. They are taking lowest of this will determine your actual CMDM gain. So these are the effect of our non-ideality or mismatch. So these things is covered. This is over. Okay, now there is a finding ICMR, or the input common mode range for a particular topology. First, let us take the simpler one. And this is VDD, and we are shorting these two input because we are applying the same voltage M1 and M2, so we can short them and apply the input. This is the VCM, input VCM. This is Vx, Vy. Suppose we are starting, we are increasing this VCM starting from 0. First we apply 0 voltage, and then we start increasing this VCM to some higher voltage. If this is 0, these two transistors have to off, will be off. It will be there, but now see what happens here. It is getting some finite VGS. VB is there. It is getting some finite VGS, but current through this is 0 because these two are off. So if we draw the IV plane, this is for M1, for M2 and M3. So M3 is having some finite VGS, but ID 0. This is the ID 3 divided by VDS 3. Not divided, VDS 3. VDS 3 means the drain to source voltage across this, and ID 3 means current through this thing. So it will start from here. And what about these two? This is open, and this point is at 0. This is open means this is at VDD. So the VDS1 and VDS2, same thing from here. VDS2 will be VDD. Okay, this is because this is at 0. This point resides here, M3. So both of them will start from some VDD. This is VDS2, VDS3. Okay. Now we are just increasing this VCM value starting from 0. So at 0, this is the situation. this transistor resides here, this one here, that one here. So we are increasing this VCM. So as we are increasing VCM, the current, this transistor after some voltage, I mean it is 0, so we have to give at least VTH, threshold voltage of this transistor, to turn this to on. So after this VTH, both of the transistor will be conducting, so they will move up, and that current will flow through this transistor. Okay, so it will also move up like this. And as the current is flowing through this line, more and more voltage is getting dropped across this resistance, so less will be available here. So VDS1 and VDS2 will be decreasing. Okay, it will like this, it will also go up. Now after some time, it will enter into the saturation zone, this M3. Say some voltage is there, it will enter saturation, and when it is entering at the saturation zone, call this as a ISS, this current, this saturation current. So after saturation, assuming ideal device, this current is flat. So even if we are increasing this VCM after that, after this point, the current through these two paths, they cannot increase, it is fixed there, so they become flat after this point. Okay, so what is the current? This current will be, this is ISS, and we are considering perfectly matched branch. So ISS by 2 will be flowing through this ISS by 2 also flowing through this. So this point will be, this particular point will be VDD minus ISS by 2 into R minus VP. What is VP? VP is that this voltage. VP means P, call this point as P. So the voltage at this point is this one, this much. So that voltage is dropped across M1. So this point, this is the VDS1. So VDS1 will be VDD minus drop across this resistance and this voltage, and this is ISS by 2. This current is ISS by 2. Now as we continue to increase this thing, this our VCM, it will move across this path, and after some time it will enter into the triode zone, both M1 and M2. Here it will be hitting here, this point, and beyond that point M1 and M2 both will be in triode zone. So this is not our intention, to operate M1 and M2 in triode zone. So we will try to restrict. And also one more thing is that we don't want to operate M3 in also triode zone. So we have to choose our VCM in such a way that M3 will be operating here and M2 will be operating here, this zone. Same thing from this zone. So this basically determines your ICMR. Lower level is this one, for that particular input voltage for which M3 enters saturation, and the upper limit is that for that particular CM voltage M1 and M2, M1 or M2 both of or any one of them is entering to the triode zone. So these two determines your higher level and lower level. Okay, now consider one more thing. Now suppose, so ICMR is this, you know the ICMR. So we can write here equation, we can write those equation here. VCM mean or VCM should be, first the lower limit greater than, VCM is this input, it should be greater than VDS3 plus VDS3 minus, okay, I should write not, okay, VDS3 is there, VGS1 prime, call it some VGS1 prime, also this is VDS3 prime. What is VDS3? VDS3 is this one, VDS3 prime this one. The input, the minimum input voltage we can apply here, this one, this voltage, suppose we are increasing the voltage and this M3 just enters here, enters the saturation zone. So this VDS3 prime will be developed here. So this voltage is VDS3, and suppose this is, and for that particular voltage, suppose this is VGS1 prime, this voltage. So the minimum voltage is this voltage plus that voltage, this plus that, okay, and this one is that, this one VGS1 prime, because for this voltage it enters in the saturation and both of this current is stuck to ISS by 2. So when it just hits this line, ISS by 2 line, this must be having some drain to source, I mean gate to source voltage VGS1 or VGS, both of them equal actually, VGS1. So when it hit at this point, that particular gate to source voltage we have to take. So this limits our input minimum VCM. Is that clear? Okay. And now consider the this point, upper point. At this point, what is happening? So here only ISS by 2 is flowing here and here, both this current. Do you have any question? You understood? This one, okay. VDS3 you understood? So it is there. Now suppose that, so we are increasing our CM from 0 to some voltage, and at a particular input voltage M3 enters here, and for that input voltage M1 and M2 has to hit this line, because after this we are assuming ISS is constant. So both of the transistors should carry ISS by 2. Now this is the ISS by 2, and there should be a corresponding gate to source voltage for this, because if I draw the M2 only, suppose this is ISS by 2 and call it this is VGS1 prime, some voltage, some value will be there. So it will be hitting at this point. We need to find the input for corresponding to that point. So when it is hitting, when our VGS1 is this one, VGS1 prime. So if we want to get the input, we have to take this voltage and that voltage, the gate to source of this one. So this voltage is this one, VGS1 prime. It is clear? So now we will go to the this point, other extreme of our zone. So now after it is hitting this point, it will continue to carry ISS by 2 here. So ISS by 2 here, ISS by 2 there. So the limit is, so now you just consider this point, this one here. It will be like this one. So VDD ISS by 2 R. This is the voltage across this point, across voltage at here Vx. Okay, this at Vx, your VDD minus ISS by 2 into R. Okay, this point voltage. So as you know that to detain this M1 in the saturation, we must have VC input, I mean VCM minus VTH of this M1 Vx. Actually we I should write it in this way, VCM minus VP. Is that visible? Minus VTH less than Vx minus Vp. This is the VD drain to source voltage. This is the VGS of this M1. Vp is this point is P. So this is the condition for M1 to be in saturation. So this condition comes to here if you cancel Vp from both sides. Okay. So your this thing should be Vx plus Vth, and Vx means this one, VDD minus ISS by 2R. This one is Vx plus Vth. So VCM should be less than this factor, and this determines the higher limit of input CM level, VCMH, and that is our lower limit. So CM level, if you plot their VCM, it can vary between these two ranges. One is the VCML, VCMH, and beyond this range, the gain, we are plotting the gain of this differential amplifier will be decreasing. So we always want to keep our diff amp to operate here. Okay, now it may be sometimes is that suppose you just you know VDD ISS by 2R, and you calculate this factor, and it may so happen that this factor may be greater than this factor may be greater than VDD. It may happen because you are adding one this VTH which doesn't have any relation with ISS. VTH is an independent quantity. So though you are subtracting this ISSR from this VDD and adding one more independent quantity which is not any relation with ISS, so this total summation may be greater than VDD in some cases. So for that case you have to take VDD upper limit, I mean VCMH as VDD, because you cannot apply or get anything greater than VDD. So this should be I should write this as a VCM VDS3 prime VGS1 minimum of or VDD. I mean whichever is the minimum, either this or that, you have to take that one. So this is your ICMR. So up to this it is clear. So now there is one more is there. Now we saw that our for M1 and M2 it varies like this. This is ISS by 2. This is our triode saturation boundary. Call it VGS1 prime. So for common mode analysis, this is our load line. This is our common mode load line. That one. Now we want to analyze the circuit from differential respect. I mean, if we assume our common mode signal as a 0, and we are giving only differential input, so how our circuit will behave? That we would like to analyze that thing, because we are using linear circuits or linear circuit components, so we can use our principle of superposition there, and principle of superposition, according to that principle we can apply VCM and VDiff or differential input separately and sum them up. So now suppose our VCM is 0 and we are applying only differential input. So if you have a perfectly matched differential amplifier, so you can bypass your current source for differential analysis. You can think this is grounded for differential analysis. This point is grounded because suppose it previously it has some finite VCM voltage. So this transistor and that transistor, they will carry ISS by 2 when no input differential input is given. Okay. And if if I make this transistor slightly more conducting, so it will carry slightly more current, more than ISS by 2. Okay, I am just increasing that voltage slightly, so that this transistor can carry slightly more current than ISS by 2, and I am decreasing this voltage slightly, and the same and by the same amount, the same amount I am increasing here, I am using the same amount to decrease this voltage. So this transistor is becoming more, I mean less conductive, so it will carry less current than ISS by 2. So what will happen, that the voltage across this point, I mean across this constant current source, they will remain constant. So the AC signal entering through this circuit, they will see this point as grounded, because there is no variation of this voltage if we fix our input common mode voltage. So we can short this one and we can analyze this circuit. Now if we short this is a simple passive resistor loaded single stage amplifier, and the load for the load line for this thing will be like that, because the RL is linear, so it will get a straight line and it will intersect this common mode biasing point somewhere. This is our actual common mode point, this intersection point, or we can say it common mode input common mode point, this intersection point. Okay. Now suppose that we are increasing, we are making this differential voltage from minus infinity to plus infinity. So first we are applying a very high voltage here and a very low voltage there, and gradually we are decreasing the difference, making this is higher and this is lower. Sometime both of them will be equal, and after that it will increase, it will decrease, and after some time we will apply a very high voltage here and a very low voltage there. It is clear? That is scheme. First we are starting from a very low voltage here and a very high voltage here to a very high voltage there and a very low voltage here. So now consider this case. We are giving a very high negative voltage at M1. So M1 will be off anyhow. M1 has to be off because we are giving a very high negative voltage here. So as this is off, so M1 will be start moving from here according along this line, and M2 will start moving from this, because as this is off, the whole ISS current has to flow through this transistor. So M2 will start from this, and this is ISS. Actually these curves are not drawn in scale. This is ISS. So M2 starts from here, M1 starts from here, here and there. And if we make this transistor more positive and this is less positive, so current through M1 will be increasing. It starts from cutoff, and we are making it less, more conductive. So current through M1 will be increasing. So current will be increased, and current through M2 will be decreasing, because as we have a fixed constant current source there. So M1 is drawing more current from this one. So current through M2 have to decrease. So this will decrease. So eventually what happens that M1 will go, when we make this very high infinite means we are giving very high voltage here, very high positive voltage here and a very high negative voltage here. So M2 will come here and M1 will go there. So they will just, it will continue from here, come over here, and M1 this way. And when both of the differential voltage is 0, because we are going from minus infinity to plus infinity, so in between somewhere it will cross the 0 line. It will be there at this point, because at this point only VCM is there, no differential input voltage. So this is the combined your ACM or common mode and differential load line. I mean picture, this what is happening there. And that I should say, okay, I have told previously that the main reason of applying or using a constant current source is to make our output independent of input common mode signal. Okay. So now just look how it is doing that thing. This is our. So I have said this is for M3. For M3 it looks like this one. It will be moving. It's not here. Yeah. So for M3 it is going like this. So for this point onwards, we can apply any VCM that will keep this M3 in the saturation. Obviously less than this one, less than this portion. So we can apply any voltage. So what will happen? Suppose you have applied some voltage greater than this. For that voltage, so if you increase your VCM, input VCM, this voltage across this M3 will change in such a way that the VGS1 and VGS2 will be equal to VGS1 prime. You have not understood? Okay, I'll suppose you are increasing that VCM here, both of this. So increasing that. beyond this point. So if you increase this voltage, so voltage across this M3 will be adjusted in such a way. If you increase this this will also increase. This point move here. I mean VP, call it VP, voltage at voltage, P point. So this point also moves along this line. So voltage across this transistor will be increasing, and that will help to maintain this particular. After all, you need this one VGS1, because otherwise the current through M1 and M2 won't be ISS by 2. You need that particular VGS1 for every input VCM. So voltage across this M3 will be changed in such a way that this voltage will be maintained at VGS1 prime. So if you are increasing your input voltage, input CM voltage, this point moves along this line. So more and more voltage will be dropped along this transistor, this one. So it will maintain this one as a constant, VGS1, and that value is VGS1 prime, which will maintain the current at ISS by 2. So this is the way how it is maintaining the ISS by 2 current for within that range, that within this range. So this is all about your ICMR and this thing. And also one thing you can look here. Suppose you are fixing your VCM here, input CM here at this point, because this will give you the point when input differential voltage is 0, and you are increasing the differential voltage difference between them from 0 to some positive value, from 0 to some positive value. So what will happen? M2 and M1 both start from this point. M2 will moving along this direction, M1 will be moving along this direction. So and after some time, or after some value of differential voltage, M1 will be hitting here. This is the triode zone, or actually these are triode saturated boundary, and M2 will be hitting here, and after this M2 will become off and M1 will enter in the triode zone. So you see there is a range of input differential voltage that we can apply, and that will help to not help, and that will make these two M1 and M2 in the saturation. Because if you increase, first assume that no differential voltage is there, so both of the transistors remain here, M1 and M2 at this point. This is the VCM, and if you are increasing that voltage, so M2 is moving here, because you are making M1, gate of the M1 more and more positive, so you are making M1 more conducting, so current through M1 will be increasing, path of this path will be followed by M1, and current through M2 will be decreasing, so M2 will be going like this, M1 will be going like that one. So there is a range for which M2 and M1 both will reside in this zone, and you see that that range is less than your VCM. This is your VCM high, and this is the range you get from your differential. So differential voltage range is normally less than your ICMR. So the range along, I mean this ICMR as well as the range along which you can apply this differential voltage is also important, and you cannot apply any voltage within this ICMR. I mean you cannot have this any differential voltage within this ICMR. You have to restrict your differential voltage within this range only, which is slightly less than your ICMR. And one thing is that you can make your ICMR negative also. For that you have to make that this point, instead of making it grounded, you have to connect it some negative voltage, say minus VDD. You are applying VDD here, you are making minus VDD here. So that will pull this range, this lower limit, to a negative value. Okay, so you can so it will be shifted there, like in this, like, so you can apply some negative common mode also. And most of your op-amp, I mean 747 op-amp, they are having this dual supply, so you can apply negative voltages there also. 741 or 7 whatever it may be, IC op-amp, good FET input op-amps. So this is all about your ICMR and differential input range, and there are some expression, I mean that those can be, what I have said along using these plots and all those things, you can derive it using your MOS expression as equation. There are finite expression, those things, I mean not numerically you have to solve all those things. You can solve these things using your simple square law MOS equation, and those some of those equation, I think in Razavi they have derived this range over which you can use this differential all those things. So you can look into those things in the book, from the book. Those are not worth discussing here. And one, I think, so finding input differential, it is over. So the final, I mean the last thing is that different types of loads. Passive load, I have discussed all those things. You can have direct connected load resistance. You can use PMOS, NMOS. As I have said in the earlier class, that PMOS have that culprit, I mean body bias culprit. I mean, so sorry, NMOS have those body bias culprit. So we cannot, we normally don't use NMOS direct connected load there. We use PMOS because that will give you higher gain. The circuit for this thing will be like this. This is a constant current source input. This is PMOS direct connected. These are all NMOS. These three are NMOS. So this is PMOS direct connected differential amplifier. And for NMOS, you have to invert those things in terminal and short accordingly. So you will be having, if we take only one part of this, you will be having gain minus. So you will be having gain this one, G1 minus G3, with M1, M2, M3, M4. So G3 is the transconductor of this M3, and G1 is transconductor of this M1. And instead, if you are using NMOS, you have to add one GMB3. There is a body bias of this one. Now, because for this you can connect the body to source, short this thing, grounded. This is also grounded. You can connect this also grounded. But for NMOS, you cannot connect the source and body connected. So NMOS direct connected load will suffer from substantial body bias effect. So it will actually what it will make, it will decrease your gain. For PMOS you have this, for NMOS you have this. So this is our, or if we use constant current source load, our circuit will look like this one. This is our primary constant current source. These two will be operating as a constant current source load, PMOS device. You can have the same current, no, okay, the same current won't do. So you should have different, one more, it will bias this one. So this current mirror will bias this load, these two constant current load, and this current mirror will bias this one. And this is a current source, this is a current sink, and both of the current are generated by your BGR circuit, these two current. And but normally what happens that for CMOS circuits, the gain of this transistor normally of the order of modern day CMOS technology 10 to some 25 or like that, 10 to 25 to 30. So which is not a good thing. So we can increase this gain using cascoding. Cascoding means we can put one cascoded transistor, and it is better to draw here. This is the cascoded current source, and this is our cascoded input device. We can use cascoded source also here for this. This is input VB1, VB2, VB3, and you have to accordingly you have to generate all these voltages from your current mirror kind of things. So you have to have three current mirror for this thing, for generating these voltages, and we are taking output from here, VO. So this cascaded current mirror will increase the output resistance. For it will also increase the output resistance, and as a whole they will increase their gain. Gain for this circuit, I mean this only simple current mirror current load, simple constant current source, is it will have a gain some G1 R1 if M1, M2, M3, M4 like this. But if you are using this cascading kind of thing, your gain will be looking like G1, G3, R3, R1, R5, R7. This is M1, M2. So you are getting much higher gain using this cascading structure. And the last thing is that the constant currents, I mean current mirror as a active as a load to our differential amplifier. This is the current mirror. Input. So this is your current mirror. This acts as a load to our differential amplifier. And normally it actually you see that this circuit is basically symmetric. I mean asymmetric one, because this transistor feels a diode connected load. But this transistor feels a constant a kind of constant current source load. So gain at this point, this is call it Vy at Vx. Gain at so gain for Vy is much higher than gain for Vx, because as I have written here, gain for diode connected load are much less than the gain of constant current source load. This is the gain of constant current source, this is the diode connected load. So these are less. So this voltage will be having much less gain than this, and normally people will take this as output, not the difference between them. And this circuit is extensively used to convert your differential input to, this is our differential input we are giving in the input, to single ended output. You know all this single ended differential output. Single ended means output with respect to ground. So we are taking so for this circuit, though it is a differential amplifier, we are not taking differential output. We just take this output of this this node with respect to ground, because the gain is here much higher than this one. It is 10 or like 10 to 15 times higher this gain. So people will take this one, and you see, and transfer characteristic of this gain, this transistor will be looking like this one, not the other one. And for rest of the transistor we have this one, rest of the diffs, but for this we will be lacking, because input here increasing, here it is decreasing like this, it will be inverted, here it will be again the same thing. So we are getting non-inverting output here, so positive gain. So the transfer characteristic of this will be showing like this one, not this. So this is your acting current mode. Okay, nothing. So you can have after this cascade structure, you can have folded cascade also. You can fold your input device in other way to reduce your overdrive, because whatever circuit you design, your transfer characteristic will be looking like, suppose like this. So they will be limited by this, upper limit will be limited by the overdrive of these transistors, and lower limit will be limited by the overdrive of this and that transistor. So if you increase this swing, if you have to decrease this overdrive, and one way of decreasing the overdrive is to you fold your input transistors. You just use folded cascade structure to increase your this overdrive, not overdrive, this output swing. And okay, one thing I should mention for this thing, this is a peculiar circuit. I mean, you cannot have all 5 transistors operating in a saturation simultaneously. It is impossible for it, because this is a current mirror. So this current mirror will try to copy this current here. So if you make this transistor more conducting, current through it will increase, and it will try to increase this current also, because it will copy the current, but you are making this transistor as a less conducting. So what will happen that, so current through both to it also increases, and current through this part also increases. So current through this device will be increases. So this device cannot be in saturation, it has to work in triode. And suppose this enters in saturation, so current through this device remains fixed, and you are increasing this current, but the current mirror will be trying to increase this current also, but it cannot do so because total current remaining fixed. So it will come out of saturation and go into triode, and so this current will be decreased. So this transistor and that transistor, they simultaneously cannot be in saturation, but the situation will be different if you connect a load here. This is unloaded. If you connect say some cap here, load cap, because in that case the unbalanced current will be, suppose I out is there, I out is flowing this direction, and suppose this now this transistor operating in saturation, so the current through is fixed, and you are making this as a this more conducting, this less conducting. So current through it will increase, it will try to copy the current, so it will current through this device will increase, but as it become less and less conducting, current through this device decreases, so the extra current will flow through this load. So for this case all the transistor can be in saturation. I mean if you connect a load here, that will balance this thing, and all the transistor then can be operating saturation. And for all our practical purpose, we normally we have to have any load, because this stage, this will have some other stage following it, and input capacitance for that stage will be acting as a load to this. So though this is a textbook, I mean unloaded kind of thing, you just explore and see what is happening, but for all practical purpose or all practical uses, we must have this load connected there. So I think this is the end. For books, you can look. Alan Holberg is a very good book. Razavi is not a good, not that good. You can read Cedra and Spitz. I think that you have that you might have following, and also Theodore Bogart. There is a very good book by Theodore Bogart. That is that actually he uses BJT devices, BJT bipolar devices to design, and discrete bipolar devices to design all of this. But the concept he explained is very beautiful and nice. So I think if you start from that book and then follow Holberg and then Razavi, that will save you time. Because if you directly start Razavi, because Razavi has made some, I mean, confusing comments, lousy statements, and all those things. So that makes the reader feeling less comfortable. So if you start reading after reading Holberg and then you start Razavi, your time will be saved, and you will be enjoy all these things reading. Okay, so thank you.